This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hello, welcome to another episode of Design Safe Radio. I'm your host, Dan Zahner, and today we are super lucky to have on the show Tara Hutchinson and Ben Schafer, the lead principal investigators on a really exciting earthquake engineering research project taking place down south at UC San Diego. And they've built a full-scale 10-story building out of cold-formed steel on UC San Diego's outdoor shake table. And it's called the CFS10 project. Starting next week, they're going to be subjecting that whole thing to simulated earthquakes to see how it performs. So really glad to have you guys here. Go ahead and introduce yourselves and let people know who you are, your name, title, institution, and then we'll get going.
Sure. I can start. Well, hello to the audience and Dan, and thank you for having me. Thank you to the Design Safe Radio, for hosting the show and allow us to share more about this landmark program. My name is Tara Hutchinson. I'm a professor in the Department of Structural Engineering at UC San Diego. I'm the lead experimental, let's say, investigator on the CFS10 shake table program. This is a capstone to our CFS NERI NSF sponsored program. It's a really great collaboration through many years between UC San Diego and Johns Hopkins.
Yeah, and hi everybody. I'm Ben Schafer, a professor at Johns Hopkins and co-PI on the team.
Excellent. Well, it's good to see you guys. Ben, we went through a little bit about what cold-formed steel is when you were on, but for people who didn't listen to that or need a refresher, can you guys give us a little bit of a rundown? What is cold-formed steel? How is it made? How does it differ from other kinds of steel building materials? And let's go on that.
Sure. So, first, always go to the back catalog and listen to as much Design Safe Radio as you can, right? So we've got a nice discussion we had on cold-formed steel. Cold-formed steel is quite literally steel which is formed to shape at room temperature. That's the cold part, as opposed to something which is hot and as typical structural steel. Tends to be quite thin because you can bend it. So less than 1/8 of an inch or around 6 millimeters or less in terms of thickness. So it finds its strength by bending it into a useful shape. Its history started out as quite similar to timber construction. So the first cold-formed steel shapes look pretty similar to 2x4s, but just the outside of them. It's grown quite substantially since then, and there are a number of different cold-formed steel products that you can use. They're in buildings already everywhere, both for non-structural and structural. And as you can see behind you and Tara, you can make a 10-story building out of it.
They're also in your car.
Absolutely, yeah. It's sheet metal, but utilized in structural engineering for useful building construction.
Yeah. And so I'm going to put my mechanical engineer hat on. I'm not a fancy civil engineer, but I spent many years watching rolls of steel go into stamping presses and get made into fenders and bodies of cars and get welded together. This is some similar technology for a less dynamic application. Well, sometimes less dynamic. And
yeah, in our case, we'll be testing that. Yeah, but absolutely, it uses the large coils of sheet steel. And as opposed to mechanical engineering where you taking individual pieces, cutting them, and then stamping them, these run through roll formers, so the coil is slit and then bent into structural shapes, channels, Z's, etc. And the way to think of it in terms of production, the shapes come out in miles per hour. So you can produce super efficiently at low energy an enormous amount of structural product. And so now you'll find, a great percentage of non-structural walls use cold-formed steel, and there's a lot of actual structural cold-formed steel. This is a multi-billion-dollar industry, so this is not a small part of building construction.
Yeah. And where is this usually made, both for this project and others? Or is this a U.S. steel, or is this foreign-made steel? Where is this coming from, and is there a difference?
So the cold forming process where you actually make the structural shape is going to essentially always be domestic. It's going to be at a location as close to the site as possible to keep embodied carbon down. For the last number of years, the steel itself would be bought on the global market. So if U.S. steel was the most competitive coil, then that's what we would have used. And then if the global market was providing at a lower rate, that's probably what they would have used as well. So it followed the economy. Of course, some changes in that world happening in the live right now. And so we're all living in that area. But there are some amazing and excellent domestic coil producers, and a key feature of domestic cold-formed steel is that it's almost entirely recycled product. So all of the domestic cold-formed steel large producers are using the waste that all of us create with the fact that our refrigerators don't last so long or our cars don't last so long to create the steel and recycle it and use it. It's one of the highest recycled rate products in the US. Really, one of the only successful true recyclability markets is steel.
Yeah, that's really interesting. And yeah, you can recycle both post-consumer cold formed steel as well as, when you're stamping things out of it, you've got all sorts.
Because it's magnetic, it's the ability to pull it out of a waste stream is quite
Yeah.
high. So the recyclability rate of steel is is the highest that I know of for any product in the US.
Wow, that's really amazing. So how did you both get into cold formed steel research? We'll start with Tara about kind of what prompted you to tackle this and some problems that you're addressing and what you hope to learn.
Sure, yeah, I'll start. Well, my interests and expertise is always kind of wrapped around the idea of using really large or really large scale testing capabilities to try to tease out the behavior of components and systems. And I've kind of always had the hat in earthquake engineering, though I've studied some other natural hazards. But using shake tables, using simulated inertial loads on actuators, running things at slow cyclic kind of simulated loads, whether they're wall or framing systems. And I've been studying a variety of types of materials, always trying to have at the backdrop, I guess, some kind of experimentation, because that's the real physical behavior can be teased out, and that can help modelers and designers and see what we've got on paper and kind of hint at the appeal towards improving behavior during earthquakes, at least. And coming into par with cold form steel is an interesting story for me. Really, Newton's law didn't go away, and CFS is so lightweight, and it's got an impressive strength and ductility potential. So over the years, there's been a lot of really great new ideas for putting this construction material together and kind of harness some of those capabilities. And if you think about seismic loads, you really want to dissipate some of that energy in a structural system. And so there's been a lot of novelties down at the component and connection level that have emerged, through other experiments and modeling work. And since I kind of have the hat on at the system level, I was really drawn towards the idea of getting these into system level tests. You have things like steel sheathed cold form steel shear walls, use of corrugated steel strapping in conjunction with kind of load bearing CFS studs, and the idea of CFS cord stud pack capability. They can get us into carrying really heavy loads, but not generating significant loads themselves, just because the raw material or the raw
Yeah, I
elements
mean,
as they're
behind you over
conformed
over your left shoulder is really interesting to see. Like, you've got an entire floor of an apartment building being lifted by a crane. Like, you can't do that
Yeah.
with I-beams.
Yeah. Yeah. And actually, this is a part of this particular study I think we're all pretty intrigued by. This is the idea that as you put, individual members together, like Ben mentioned, wood framing can come together in individual sticks. CFS can come together in individual sticks, and practice has figured out the most efficient, effective strategies to do that. But we've got a lot of novelties in construction practice trying to put CFS together in panels, so two-dimensional elements. And we thought, well, the community wants to try to get modules out there. They want to get volumetric elements out there. It's more efficient on site. And so we explored that in this project too. So I chose this particular image because here we are lifting up one of those volumetric modules. It weighs probably 15,000 pounds, and it's about half of the test specimen that is actually modularized.
Wow.
But my story goes back to actually studying cold-formed steel partition wall behavior in a in a concrete building. Actually, I was really interested in non-structural interactions, and so as I think Ben mentioned, a lot of the early work started out with lightweight interior partitions, and these are non-load bearing, but they have significant implications in the earthquake response realm. They can draw down the functionality, really limit return to operability and things like that. So those can have significant consequences when we think about performance of buildings, and particularly when we get into really important buildings like hospitals. We need to get
Yeah.
back into the hospitals. We need to have them operable. So I worked in 2012, I worked with colleagues here on a building non-structural components and systems program, and we had CFS balloon frame facades and interior partition walls, and tried to tease out, capturing the behavior of sliding connections and other things. That led to a lot of interesting things on, let's say, the non-load bearing side of things. The table, by the way, was in a one-dimensional configuration at that time, so we could really
Yeah.
only study things sort of in plane, at least. But then I think Ben was talking about, CFS structural codes have evolved, and a lot of his work has really embraced that and helped propel that forward in that community, and the realization that it's such a great material from a structural perspective. So I was really actually inspired by a lot of the work that Ben and Professor Kara Peterman did on low-rise buildings and trying to put together cold-formed steel shear walls with wood sheathing on a low. Their capstone to their effort was actually a two-story. I think coined the CFS NEAS program was conducted at Buffalo. And we thought with the panelizers and expertise out here, we thought, why can't we really push this, to a taller and taller structure? So in 2016, a few years after Professor Peterman's and Professor Schafer's tests, we were able to get some resources to conduct a six-story cold-formed steel program here at San Diego. At the time, though, the table was in one-dimensional configuration as well. But at least that program complemented, the low-rise system level study, really enriched it a bit more. It also embraced the idea of adopting steel sheathing overlaid by CFS studs. We were able to get some architectural finishes in the system, and realistic openings like you'd see in, architectural buildings with doors and windows and other things. But definitely did not have the high fidelity that we dreamt of later when Ben and I got together and concocted this with our industry realization wrapping us up.
Yeah, and that's a perfect segue. You're wonderful to interview. You just set me up perfectly. How did you and Ben get together? I mean, Ben, will let you, kind of refresh the audience a little bit about your background, and then get into how you guys connected on this crazy thing.
Yeah, so cold-formed steel, or CFS as we've been referring it to, was the topic of my PhD, and now I'm old, so that means 30 years ago. So I've been working in the cold-formed steel industry at a variety of levels for my entire career, really focused on enabling engineers to use this thin material. So I've really been attracted to the efficiency that you can create. That efficiency requires more engineering than might be typical. And so that balance between doing more engineering and getting the reward of it has been the sort of the story of cold-formed steel and how it's grown for a number of years. When you look at where it could go to, you start thinking, how can you build it faster? How can you build it more resilient? How can you build it taller? You sort of look at all these sort of limitations and how you can push on them. And really, seismic is the best place as a hazard to really get your mind around the large deformation, high demand situations. Everything else is more kind of in the service range, and you can kind of work it out. So I've been attracted to that sort of high seismic hazard for a number of years. And was super interested in trying to push the envelope on what we could do to model and test a really landmark, taller cold-formed steel construction. So if you're interested in doing that, there's only one organization you can go to. That's NSF, because that's the only place that you can get access to a facility which would allow you to test at that kind of scale. If you look at the environment of people that might be able to help you and collaborate with you on such a test, There's like 3 or 4 on the planet. Tara's my favorite. So it was an absolute pleasure to sort of reach out to her. This is like 10 years ago. She had just finished up CFS HUD, and we started having some conversations. We were assisted a little bit by a wonderful AISI and AISC staff member, Bonnie Manley, who deserves mention.
What's AISI and AISC?
Oh, that's American Iron and Steel Institute and American Institute of Steel Construction. Yes, thank you for acronym police.
We all live in an acronym soup, and sometimes we got
of course it's engineers,
people are in
right?
different bowls of acronym soup.
It's engineers what we do, but so kudos to her as well for helping connect us in early days, and then we were able to have a lot of discussions that led to what was a proposal a very long time ago to begin our journey for this particular project.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NARI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NARI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.